So now that you have a better understanding of the concepts of concurrency, synchronization, and parallelism, let's kind of give you a tour through the history of all this stuff as it pertains to Java. So we'll look at the history of concurrency and parallelism over the years. You might know some of this if you program with Java quite a bit. You may not know any of it, so that's okay. We'll learn it together, or I'll teach it so we all learn together. So when Java first was released in its modern form, it had an earlier start in the very early 90s as part of something called Oak, which was an internal project at Sun. But when it finally hit the streets in 95 or so, 95 time frame or so, as Java 1, it had support for foundational concurrency mechanisms. And these were things that were implemented by the Java execution environment, for example, the Java virtual machine. And the core thing that came out with Java 1.0, if you're interested in knowing the history, was threads and built-in monitor objects. That's what you got out of the box with the first release of Java. The focus was on very basic multi-threading and synchronization primitives. Nothing fancy, nothing special. Here's a couple examples of how this might work. So here we're going to have a simple queue, which you can see the code that goes along with it here. And the simple queue is a correct, not buggy, but a correct bounded blocking queue. And what that basically means is that if you try to remove an item from the queue and it's empty, it will wait. The call to take will wait. If you try to put something into the queue and it's full, the call to put will wait. So that's, and it waits correctly. It doesn't end up blowing up in some bizarre way. What we do here is we create the simple blocking queue, and then we go ahead and make two threads. One thread is a producer, which will put stuff into the queue. One thread is a consumer, which will try to take stuff out of the queue. And once we create those two threads, we go ahead and start the threads. And then after they're started, we go ahead and let them do their thing. And the main thread, the thread that set the wheels in motion, will join with those threads. Join is a very simple example of something called a barrier synchronizer. So it will wait here for these threads to finish, these threads that are started to finish, and then after they're done, it will continue on its way. So those are kind of the basic mechanisms from threading point of view you get with Java 1.0. You also get some very simple synchronization primitives, mutual exclusion and coordination via something called a built-in monitor object. And here's some examples of a built-in monitor object. This is a little snippet of the simple blocking bounded queue class, which has a synchronized statement. And synchronized simply means only one thread at a time can be in this code executing in the critical section. And what happens here is if you're trying to take something, then while the list that implements the queue is empty, you have to wait. And when you wait, that atomically releases the synchronized lock, the so-called intrinsic lock, so someone else can get in the critical section, and puts that thread to sleep. And once you've gotten yourself through this guarded condition, this is called the guarded suspension pattern. Once you get through here and the list is no longer empty, then you're going to notify anybody who's waiting for the list to be no longer full, that you're taking something out of the queue, and then you remove the first item from the list and release the lock on the way out. So those are the basic mechanisms that are available. For those of you who've taken the other concurrent object-oriented programming course, this should look familiar. So what were the good things? The good things were that the built-in concurrency mechanisms, threading, and built-in monitor objects were very efficient, but low level and very limited and very error prone. So it's all kinds of mistakes can arise when you write code at that level. In particular, there's lots of things called accidental complexity. So you can have deadlock, you can forget to lock things, so it's easy to have code that will have race conditions if you're not really careful, and you end up with all kinds of threads running around. It's very complicated, as is only the case, as is almost always the case when you write concurrent programs. With Java 5, which came out around the 2004 timeframe, they added a boatload of concurrency and synchronization mechanisms to Java to help alleviate some of the limitations with the Java 1.0 support for threads and built-in monitor objects. So they have this cool thing called the executor framework, which is basically thread pools. They have a whole pile of new synchronizers, reentrant lock, semaphore, condition object, and so on and so forth. Those are more powerful than the mechanisms that are built into the Java virtual machine. And in fact, all these things are implemented as packages on top of the virtual machine layer. They have atomics, like atomic int, or atomic integer, atomic long, atomic boolean. There's concurrent collections, like concurrent hash map, and so on and so forth. There's a whole pile of blocking queues, link blocking queue, array blocking queue, and so on and so forth. So lots and lots more stuff was added in Java 5. The focus in that era was on so-called coarse-grained task parallelism, where computations can run concurrently in background threads. So a good example of this would be the concept of a thread pool, where you've got a pool of worker threads and some queues, and there's an executor completion service. And what can happen here is that a program can come along and submit tasks to run in the worker thread pool concurrently, and then as those tasks are finished, the results are stuck onto some internal queue called a completion queue, and then application code can pull the results off and do the next step in the processing. So that's kind of the model of programming there. Here's a very simple example that's a variant of some stuff we'll do in next semester's course with something called a Palantir E Manager. Anybody here who's a Lord of the Rings fan remembers the Palantir, which was this seeing stone you can gaze into to communicate. It's kind of like an ancient magic walkie-talkie, and it's an ancient Skype system, I guess. And so basically, we have this program where you spawn a bunch of Palantiri, and you have a bunch of beings, and then the beings take turns gazing into the Palantiri. So to make this work, we create ourselves a fixed size pool of threads, one thread per being. We create these things called cyclic barriers, which are barrier synchronizers to control the starting and stopping of the gazing into the Palantiri. And then we go ahead and execute these beings to run and access the Palantiri. There's always more beings than there are Palantiri, so you have to share the resources wisely and efficiently. So that's an example of some of the mechanisms that are available with Java 5. So thread pools, different kind of synchronizers, much more powerful set of coordination and mutual exclusion mechanisms. So this was good, very feature-rich, very highly optimized, very clever patterns and clever optimization and implementation techniques. However, still relatively tedious and error-prone to program, because you're essentially doing shared objects and/or message passing with concurrency. So life is still perhaps more complicated than we might want. And it didn't really scale up as much as we would like to the emerging multiprocessors and multi-core processors. So this type of stuff was really intended for systems with a small number of cores or a small number of processors. So as more processors became available towards the latter part of the 2000 era, they needed something else. So what was that something else? Well, that something else was the first foundational parallelism support that came with Java 7. Remember, Java 7 was released about a decade ago, around 2010. And one of the major contributions of the Java 7 era support for parallelism was the fork join pool, which is also implemented as a set of classes on top of the underlying virtual machine. And the fork join pool is really cool. It focuses on finer grained data parallelism that will have multiple cores running the same computation on different data elements. So this is what's typically called data parallelism. So you take your data and you split your data up into chunks, and then you have your task, and the same task runs on every piece of data. My favorite example, this is sometimes called SIMD, single instruction, multiple data. My favorite example of this is taking your clothes to a laundromat or to the laundry room in your place of residence, where you've got 12 washers and dryers, and running all your load of laundry, which you've probably procrastinated washing for some time, splitting them across all the different washers and running them all in parallel. That's a classic example of data parallelism, because you get all these things running at the same time. They're all doing the same thing. They're doing wash, or then later they're going to do dry, but you all do them in parallel. And there are no dependencies between them. You don't have to, stop one load and then take something out and put it in another washer, right? They just all run independently. So that's what data parallelism is. And the fork join pool supports this by this capability of taking a big task and forking it into smaller tasks, running all those smaller tasks in parallel, and then joining them together, just like we talked about before. So this is sort of the canonical realization of fork join processing or parallel computing with that split, apply, combine paradigm we talked about before, just done with Java. There's an example that shows how this works that you can get access to here in my repository, where we use the so-called common fork join pool. In Java 8 and beyond, there's a single common pool that's always available for everybody to use. And we'll talk about why. There's one of them later. And we can go ahead and run a bunch of searches in parallel, looking in this particular case for phrases in the complete works of Shakespeare. So if you've ever wondered, who said, or where was it said, my horse, or my kingdom for a horse, my kingdom for a horse. You can use this program to tell you where that appeared. Or, other famous quotes like, to thine own self be true, or neither a borrower nor a lender be, or what light through yon window breaks. You can use this program to search the complete work of Shakespeare in parallel using the fork join pool to do that. This framework is very powerful, very scalable, but somewhat tedious to program directly because it's still an object-oriented world and you have to do the splitting of the tasks yourself manually, and you have to do the joining of the sub-results manually. So it's really cool, but a lot of extra programming. So where does that lead us? With Java 8, they finally took the peanut butter of fork join pool and they combined it with the chocolate of functional programming and ended up with the tasty Reese's peanut butter cup combo of the best of both worlds. And so the key contribution with Java 8 was this concept of parallel streams, which is functional programming wrapped around the fork join pool framework, and then this other thing called Computable Futures, which is not quite the same metaphor, but it's pretty cool. So what happened there was that they gave you functional programming support, in other words, programming with functional programming features and concepts and APIs, to do fine-grained data parallelism, and the parallel streams framework is what you get with that. And you also get reactive asynchronous programming with this thing called the Computable Futures framework. And we'll talk, of course, about both of them. Parallel streams are a little easier to reason about than Computable Futures, but Computable Futures are typically a little faster. They're both super cool. And here's an example of using parallel streams to synchronously download a list of URLs from remote servers, ignoring the ones that you've already downloaded before, downloading the ones you haven't downloaded before, and then applying image filters to transform them and to do all these things in parallel. And this is a really clean, relatively simple to understand once you know how to read the syntax way of doing this, and it scales up quite nicely. There's also ways of doing the same sort of thing with asynchronous processing. And in fact, you can actually combine the two things together. So here's a place where we're using a sequential stream instead of a parallel stream, but we're combining this with asynchronous processing using Computable Futures. And you'll get a sense of how all that stuff works a little later. So the cool thing about these parallelism frameworks is that they strike a really nice balance between programmer productivity on one hand and computing performance on the other. And that's always been the elusive holy grail of developing systems and software. Historically, you could get human productivity by using higher level languages at a cost to performance, or you could get performance by programming with rather low-level APIs, like assembly code or C or something horrible like that. And the cool thing about the modern world that we live in with languages like Java that have features like support for parallel streams and computable futures and fork join pools and so on, is that this distinction between productive for humans and productive or performant for computing hardware is largely going away. So more and more things can be done perfectly acceptably by using modern languages and modern tools. Now, there's still the occasional application like the nuclear reactor temperature control system or whatnot to keep the water cool in the reactor core that still needs low-level programming with C or assembly code, but that stuff is becoming fewer and fewer and farther between. And especially with the proliferation of modern multi-core hardware, increasingly it's all about knowing how to take advantage of software frameworks like parallel streams, like fork join pool, that can be used to speed things up, because that's going to get you a lot more bang for your buck than programming in assembly code, because you're getting micro-level optimizations and missing the ability to take advantage of all the parallelism available on modern hardware. However, one of the downsides with the frameworks we talked about is they can be a bit prescriptive. If your problem really maps nicely into a divide and conquer style or map-reduce style of programming or split, apply, combine style of programming, this stuff is awesome. But if it doesn't always fit quite right. So I think that's where we're going to stop for the day. We still have another discussion where I'm going to go and kind of compare and contrast all these paradigms we just talked about. We will do that on Monday, and then we're going to start really getting into how to program functional programming in parallel with Java.